Hello, everyone. This is our next to the last meeting for our online lab. We actually finished the labs not last week, but the week before. I've been using this time to, well, for starters, for grading, but also for you guys to have a chance to have a question and answer sessions, that sort of thing. So I'm here again. That being said, I haven't had really anybody show up for these, so I've prepared a lecture as I always do. So in this case, I'm actually just going to make it into a single problem-solving example where I basically solve or calculate the moment of inertia for a thin rod through two different axes and through three different ways, basically two versions using the calculus and the third version using the parallel axis theorem. So to that end, let me go ahead and share my iPad screen with you and we'll just move along as if everything is normal. So I've actually written up this particular example. It says a thin, long rod of length L has its mass M uniformly distributed along its length. Use calculus to calculate its moment of inertia if rotated about an axis perpendicular to its length and through its geometric center. In other words, through its center of mass, but since it's uniformly distributed, the center of mass is the geometric center. Uh, also repeat for being rotated about one end and also verify that the parallel axis theorem gives the same result for it rotated about the end. So we're going to go ahead and do this. I'll start off with writing my solution. This is where, again, you should probably start your problem by writing down information you know. We know the mass of this object is m. We know the length of this object is L. We know that in general, dm is supposed to be equal to lambda dl, or dm is supposed to be equal to sigma dA, or dm is supposed to be equal to rho dV, where dl is a differential length, dA is a differential area, and dV is a differential volume. Basically, what it means is when we're integrating over an object that appears in some sense one-dimensional, meaning it has, like in the case of a rod, this would be somewhat of a one-dimensional object in that this length right here is well under 1/10 of the total length left and right, and the length from front to back is also well under 1/10 of the length from left to right. So in some sense, you could treat this as a one-dimensional object. You can treat a business card or a uh, bookmark, for instance, that my daughter made for me, or actually my daughter bought this one. But you could treat this object as a two-dimensional object because you can see that it clearly has a left, right, and up, down dimension, but the thickness dimension is well under 1/10 of either of the other dimensions. So this would be a good example of a two-dimensional object. And then, of course, the row is when you have a three-dimensional object where all of the dimensions are at least in some sense comparable to the other dimension. If the mass is actually uniformly distributed, that means either lambda, sigma, or rho is a constant, and we're going to use that. Now, what we do know is this rod has a length L, a mass M, and it's uniformly distributed. That appears, since I told you that it's a thin, long rod, that appears to recommend that we use the rod as if it's a one-dimensional object, in which case the lambda, which you can look at dm equals lambda dl to figure out that lambda is dm over dl, which if it's uniform, you really just have to take the total mass and divide it by the total length. And that is, in fact, lambda is equal to m over L. So we'll make use of that. Now I'm going to, just so we can have coordinates to point to in variables like x, y, and z to use, I'm going to go ahead and draw a coordinate system and put this particular object in it. So let me start off by drawing a XY coordinate system. That looks pretty good. Actually, I should probably go one more block so I can split it up evenly. Now, what we're doing here is we're imagining that the length of the rod is actually L. So this side, which is 4 squares away, and this side, which is 4 squares away, are the two ends. This end is at L over 2. And actually, my program is trying to make my writing better by thinking I'm drawing specifically drawings as opposed to numbers. So that's where the rod is going to lay. I'm going to say this is my x-axis, this is my y-axis, and this is for the first part. So what I'm going to do now is, oops, I need to change colors. What I'm going to do now is draw the actual rod thin like it is, so you can see that the vertical dimension, which is very similar to the in and out dimension, are both very, very teeny. This actually looks like I might have drawn it just a little bit, well, not exactly the top and the bottom of the rod are parallel, but that's close enough. So what we're also going to use is the fact that the moment of inertia is given by the variable I, and that variable I can be expressed in integral form as r squared dm, where r is the distance from the differential mass element dm from that mass element to specifically the rotation axis. In this case, in part A, this y-axis is the rotation axis. So this is the rotation axis for the first part. Okay, so if I look at the rod, and normally it's smart when you're doing this sort of thing to start in on the x-axis, on the y-axis, or in the first quadrant, because otherwise you got to watch out for negative signs and stuff like that. So I'm going to take a differential mass segment over here on the positive x-axis, which is again what I'm saying when you should do it in the on the x-axis. I specifically mean on the positive x-axis or on the positive y-axis are in the quadrant between those two. That's where you should start. So what I'm doing right now is I'm suggesting that this particular width from here to here is a width dx. And this particular width from here to here is our r. And since that r happens to be along the x-axis, we can just replace r with the x-coordinate, because we know any point that has an x-coordinate, that x-coordinate basically is the distance between the y-axis, which is the rotation axis, and the object. So that is our little dx, and in fact, that little blue spot is our differential mass element. So we'll say dm is equal to that guy lambda times that guy dx. I was saying that guy because I was going to say dx first. But anyways, it's basically lambda times the thickness of it. We're calling that little slice of this rod the differential mass element. So all I have to do is substitute what I have now discovered and determined, and that is specifically that we're going to integrate from x equals negative L over 2 to positive L over 2. The distance to the differential mass element is x, so we're going to integrate x squared, and the differential mass element is lambda times dx. And we already know lambda is m over L, but we'll keep it as lambda for right now. We'll pull the lambda out in front, and we'll get lambda times the integral from negative L over 2 to L over 2 of x squared dx. And of course, the integral of x squared dx is actually 1/3 x cubed. So this is going to become lambda over 3 times L over 2 cubed for the top range of integration, and then minus L over 2 cubed for the bottom range of integration. So with that in mind, we can now do the math. This is going to be, remember, lambda is m over L, so I'll go ahead and say that's m over 3L. And then I'm going to take the L over 2 that's cubed, and that's going to become L cubed over 8 minus now the negative L over 2. When that's cubed, it's negative times a negative gives a positive, but then a negative again gives a negative. So it's going to be minus the negative L cubed over 8. So minus a negative is the same thing as plus a positive. which we often write in pre-algebra and algebra 1 and algebra 2 like that. We now know that we have 2L cubed over 8, which is the same thing as L cubed over 4, and 4 times 3 is 12. So also L cubed over L is just L squared. So we get the final answer, which is the moment of inertia about the end. Dang it, I go writing in the wrong color again. The moment of inertia about the end is actually equal to 1/12 mL squared, and that's moment of inertia about the center of mass. I think I might have just said N for some reason, but the moment of inertia about the center of mass is equal to 1/12 mL squared. That was the first part that we're looking for. Now, if we wish to rotate it about the left end, it might be smart to draw another coordinate system, and I'll do that really quickly just to set it up again. So again, we're going to draw another coordinate system. This time I'm putting the y-axis right here, and 1, 2, 3, 4, 1, 2, 3, 4, and I'm putting the x-axis right here. And what I'm going to do is say that the rod is actually from the origin to this particular location. And this particular location, of course, is just plain L. And of course, this rod goes all the way to this end too. And this is our x-axis. This is our y-axis, but this is also our axis of rotation. So I will choose a differential mass element again, either along the y-axis, the positive y-axis, or along the positive x-axis, or in the first quadrant. In this case, I am again choosing along the positive x-axis. I'm going to do it in red, I guess, because I just did that. This distance from the right side of that little differential mass element to the left side is going to be dx, and this little thing is actually the differential mass element, and that will be given by lambda times dx. So now we can do the integral again. So this is the integral about the end, or the moment of inertia about the end, which equals the integral of r squared dm. You can see, in fact, that the distance from here to here is actually x, but that also qualifies for what we would call r, the distance from the axis of rotation to the actual differential mass element. So we now know that we can write this as the integral of x squared lambda dx, which is lambda times the integral from 0 to L of x squared dx. And of course, the integral of x squared dx is 1/3 x cubed. So this is going to become lambda over 3 times L cubed. Now we can go ahead and plug in that the density is mass divided by length, and then we're going to multiply that by, of course, L cubed over the 3 that was already there. And you can see, of course, that this exponent of 3 becomes an exponent of 2 when it cancels out the L. So finally, we have that the moment of inertia about the end is equal to 1/3 mL squared. And again, this is exactly what we expect for a uniformly distributed rod, or a uniformly distributed mass of rod rotating about its end. Both of these formulas we found so far are completely consistent with the table that the books gives, but now I wanted to do the third part, which is use the parallel axis theorem to show that the moment of inertia about the end is in fact this 1/3 mL squared. The moment of the parallel axis theorem, which I'll just write as parallel axis theorem, okay, that is the moment of inertia about a parallel axis is equal to the moment of inertia about the center of mass plus the mass of the object times the distance between the center of mass and the parallel axis. That has to be squared. So we can look at this and realize that when we did the center of mass one, we got 1/12 ml squared. But now we have to add the m times b, where b is the distance from the new rotation axis to the other rotation axis. The other rotation axis was at L/2. Now we're going over to here. So this distance b is equal to L/2. So with that being said, I'm going to put in L/2 because that's how far the center of mass axis is from the end of the rod axis, and that has to be squared. So I'm going to get 1/12 ml squared plus 1/4 ml squared. So I about the parallel axis, which is also equal to I about the end, turns out to be ml squared times 1/12 plus 1/4. Least common denominator, of course, is 12, so I need to multiply this by 3/3. And when I get that, I can now say we basically have 3/12 plus 1/12, which is 4/12 ml squared. But 4/12, of course, is 1/3 ml squared. So now we have demonstrated the claim. So we write QED, which does not mean quite easily done, but that's one of the ways we use it. And it also doesn't mean quantum electrodynamics, even though we do use it for that. It's quod erratum demonstratum, or something along those lines. Might be misremembering a couple of my Latin suffixes. But either way, we now have that the answer is, in fact, 1/3 ml squared, and hopefully that shows you how to do it. That's it. I don't see anybody here yet, so I'm going to go ahead and kill this and maybe start another video. Bye, everyone.